over to our next speaker, who will highlight Eddington in another way.
So, given the last kerfuffle, I guess I'll skip PowerPoint altogether. Thanks for sitting through a long day to the last paper. I'll try to keep things not too long to keep people awake. I want to start off by reminding everyone that 100 years ago, there were no cosmologists. Okay? There were people who studied the cosmos, but they would have been called astronomers or physicists or mathematicians. Cosmology wasn't really a discipline yet. And what that meant was there was no agreed upon training, no agreed upon set of methods, no agreed upon set of goals, or even what it was that you were looking for when you were studying the universe. And that made it very difficult to arrive at the point where people were willing to accept that the universe was in fact expanding. So I'm going to be talking about essentially from 1915 up through 1930 or so, this point when it wasn't really clear what one did when one wanted to study the universe. An important part of the sort of disciplinary issues I just referred to is the relationship between theory and observation. Again, the people who did observation at this time and the people who did the theory at this time were very different sorts of folks. So when they got together to talk to each other, there was disagreement about what theory could explain, and there was disagreement about what the observations meant. So throughout the 1920s, we see again and again that the meaning of both the theory and the observations was highly ambiguous. So I'm going to talk about just about Eddington today for the most part, and the reason I think he's useful for this is that he helps us show a lot of these difficulties, that is, the various disciplinary splits, the issues between theory and observation, and also how he helped to overcome those difficulties to get to the point where we believe in an expanding universe. Eddington at the time was the Plumian Professor of Astronomy at Cambridge. He had an unusual background. He studied physics at Manchester, and then mathematics at Cambridge, and then he was the assistant to the Royal Observatory. So he had deep experience in physics, sophisticated mathematics, and observational astronomy, which not many people had at the time. So this diverse set of skills, as well as his personal and professional contacts, made him really just the right person to try and grapple with these difficulties of early cosmology. I'm going to start off talking about de Sitter's theory, and both Cormac and Harry did such a nice job introducing the theory that I'm just going to skip it and assume you were paying close attention to them, because they did such a nice job. I think Peter just pointed out, that de Sitter's theory comes to the astronomical community through Eddington. The letters literally appear on his desk, and then Eddington arranges for their publication. That was pretty standard for relativity at this time. Eddington was sort of the nexus. Papers come through him. He interprets them for people unfamiliar with the ideas of the math. He popularizes the concepts of relativity. And one of the big issues that he seizes on right away is this question of the de Sitter effect. And the de Sitter effect is often sort of put in the textbook as one of the first inklings of the idea of an expanding universe. But at the time, as has come up earlier, it's extremely ambiguous about, first, what de Sitter actually predicted in his theory, and second, how we might actually find it. And part of the problem was that there were apparently two separate phenomena that were labeled under the name of the de Sitter effect. The first is that if you take a de Sitter universe, which is empty, and you put two particles in, they recede from each other. So you could imagine getting a Doppler redshift from that. And second, this just comes right out of the relativistic equations, things at the edge of the universe, if you're at the center, if you're the observer, things at the edge of the universe appear to be redshifted due to a time dilation effect. That is, it's a purely relativistic redshift effect. Now, it was not at all clear that these had any relation to each other. Just from looking at the relativistic equations at the time, there was really no reason to think that these were connected in any way. They seem to be two completely different phenomena. So Eddington grapples with this actually right away. In his very first publication, major publication on relativity in 1918, he writes a short book, The Report on Relativity, for the Anglophone world. And in particular, he knows about Slipher's work on redshifts. So he's thinking about this observational work on redshift at the same time he's trying to understand exactly what's going on in de Sitter's theory. And it's very clear that he really has no idea how to bring these things together. He's got some observational redshifts, he's got some theoretical ideas about redshifts, and he's just not sure how they should fit together. When he first brings up the theory, de Sitter's ideas, he says, quote, "The most interesting application of this hypothesis," that is de Sitter's model, "is in connection with the very large observed velocities of spiral nebulae." So that suggests he's thinking in terms of physical movement. It's quite clear. But then on the next page, he notes that de Sitter's theory predicts a redshift, which he notes that astronomers would interpret this redshift as a great velocity of recession. But then he points out that it's not really clear whether the redshifts are universal and whether or not the recession is actually predominates as opposed to blue shifts. So in the end, he ends up calling radial velocities spurious. So that suggests that he's interpreting the de Sitter effect as a purely relativistic effect and saying that attributing the redshift to motion would be a mistake. So he just leaves it there, because it's unclear what's actually happening. 2 years later, he writes one of his first major books on relativity, space-time and gravitation, and then he tries to grapple with this again. He says, okay, we know spirals are the most distant object known, and de Sitter says things at the edge of the universe should experience a relativistic redshift. So we should check and see, and he notes that Slipher has already done this, and that astronomers would normally interpret such a redshift as a Doppler effect. But then he steps back again, and he says, since the de Sitter's world has this additional relativistic effect, it's not quite clear. So he puts it this way, quote, this may be a genuine phenomenon in the evolution of the material universe, but it is also possible that the interpretation of spectral displacement as a receding velocity is erroneous, and the effect is really the slowing of atomic vibrations predicted by de Sitter's theory. So on one hand, he seems to be pulled toward a Doppler interpretation by Slipher's observations, but the alternative interpretation of de Sitter's effect keeps nagging at him. He eventually decides that the purely relativistic interpretation of the de Sitter effect must be wrong because there are these paradoxes that arise with round trips between the center and the edge of the universe and back again. His second book on relativity, The Mathematical Theory of Relativity, he then emphasizes this particle repulsion property of the de Sitter's model as a point in its favor. He says that is, you should believe the de Sitter theory because of this perplexing problem of cosmogony, the great speed of the spiral nebulae. So then he's willing to accept a preponderance of high velocity recession after corresponding with Slipher for some time. But again, he notes that de Sitter's theory gives this double explanation between the scatter and the relativistic effects. And again, he notes that it would be very easy to erroneously interpret the relativistic effect as a motion of recession. He's thoroughly confused by 1923, I think is the right way to think about this. At one point, he actually tries to sort of split the difference between the two effects with what he calls his anticipation idea, in which he says that at the moment the light leaves the distant spiral, the spiral shouldn't be thought of as moving at all, but by the time we see the light, it will have been accelerated via the other de Sitter effect to the speed at which is appropriate for the redshift we're now seeing. So if that makes any sense to you, let me know, because it's not really clear to me what he thinks he's explaining with this. I think he's just mentioning this as kind of a mathematical curiosity. He never mentions it again after this. So he's certainly not persuaded by the mid-1920s that the universe is expanding. He repeatedly uses Slipher's measurements, but he's not sure about the relationship to general relativistic world models at all. As we've seen a couple of times, that very nice table from his book of Slipher's unpublished observations. So he's got this great data, and he's got these interesting models, but he's still not sure what kind of a connection he can make. It's worth noting that at this point in the mid-20s, it's really a choice, seems to be a choice between two possibilities. Either the de Sitter model, in which the universe is empty and has these strange redshift effects, and the Einstein model, in which there's stuff, but it's static, and nothing very interesting is happening. Many people looking at the theory at the time tried to make the case that these were completely different ways of looking at the universe, and there's no real relationship between the Einstein and the de Sitter models. Eddington disagreed. He thought of them as limiting cases. There was matter with no motion and motion with no matter, and somewhere in between there must be a real universe. So he sort of puts out the call, saying someone needs to figure out what the real universe must be in between these. In terms of comparing them, he says the Einstein universe is more interesting for physicists. That is, there's more interesting physics going on with relativity. It also gives rise to these large number coincidences that I'll say more about later. But on the other hand, he says the de Sitter universe is more appealing for astronomers. And in fact, he uses this. So when he writes to Shapley in 1918 about the de Sitter theory, he tries to get him excited by saying, look, you know that mysterious redshift that Slipher's found? Well, I think we have someone who's explained what's going on there. So he tries to sell it to astronomers that way. In the end, this is mid-20s, he decides that de Sitter's hypothesis is slightly better, but one of the problems is that most of the theorists of relativity at this time are still Machian, like Einstein, and in the Machian idea of relativity, inertia only comes from the presence of other matter in the universe. So if there's no matter, then you can't have any inertia or any kind of relativistic effects. So it's kind of a non-starter for many of the physicists at the time. So it's not clear to Eddington that the observed redshifts could be considered in any meaningful way without theory. That is, they were just observations at this point. This changes by the early 1930s. The obvious benchmark might seem to be Hubble's observations, but that definitely wasn't the case for Eddington, nor many other folks, as the discussion today has shown. Eddington was not particularly excited by Hubble's observations. He actually refers to Slipher's results right through the 1930s. He sees those as the core things that he needs to think about. So he's really only willing to accept an expanding universe as a result of theoretical developments, not new observations. He'd been arguing for years that neither the Einstein nor the de Sitter worlds were quite right. So the intermediate solutions he was looking for finally start popping up at the end of the 1920s, even though he realizes that they had been written several times before that. And looking back later, he says, it's amazing that these solutions were found, published, and forgotten, buried like a needle in the haystack of relativity literature. And he thinks about why this happens, and he actually attributes the problem of some of these papers just kind of disappearing into the mist is that they were written for very specific disciplinary groups. That is, Robertson, for instance, he says, is too mathematical and logical rather than astronomical. So therefore, the astronomers who knew about the redshifts didn't bother reading any of these technical mathematical papers because it didn't look like there was anything interesting to them there. Lemaitre's paper resurfaces in 1930. I think we've got a speaker on Lemaitre tomorrow, right? So hopefully I won't bother telling that story. When it finally resurfaces, Eddington gets very excited and tries to make the paper widely known. He gives it special publication because it seems to resolve exactly the Einstein versus de Sitter problem, exactly what he'd been worrying about for the previous 10, 12 years. And he attributes Lemaitre as the reason. Lemaitre was the person who made us think that the universe is expanding. So I said that because he doesn't use the word discovery, but he says mainly due to Lemaitre, we think the universe is expanding. He credits de Sitter with providing the first hint of an expanding universe. He said we should think of it this way. He said de Sitter gave us an expectation that distant objects would be moving away from us, or, quote, at least that they would deceive the observer into thinking they were moving away. It seems he's a little bitter about the years of confusion there. So he dismisses de Sitter's theory as minor importance by 1930, but he says it got us thinking a particular way about the problem. He says that's the critical thing. So he says now we have a genuine recession of celestial objects, not just the imitation recession of de Sitter. Once he fully converted to the idea of an expanding universe, Eddington loved to stress how weird it was, right? Trying to stress how different this was than any other previous conception of the universe. Did this many different ways. I like this one. The theory of the expanding universe is in some respects so preposterous that we naturally hesitate to commit ourselves to it. It contains elements, so many elements so incredible that I feel almost an indignation that anyone should believe it, except myself. And what he's talking about there is issues that have come up a couple times today, is that the speed of the receding galaxies are enormous, which suggests that the size of the universe is enormous beyond any previous comprehension. And also, the question of the time scale gets thrown all off. That is, the age of the universe that astronomers had been used to working with was suddenly quite different, and no one was quite sure how to grapple with these things. So by 1930, he's decided that there really is a genuine recession and that this is related to Lemaitre's model. Hubble's observations get pushed to the side again. He calls them disturbing, and that there is a natural hesitation in accepting them at their face value, not because he's critical of the large error bars, although he was, but rather that he says we can't understand these without a proper theory behind them. So he says over and over again that theory was the key to making the expanding universe real. He said it would be a mistake to regard the expansion of the universe as an observational phenomenon independent of the theories of curved space. He says rather these theories were all constructed either when the measurements of recession were few and unclear, or by people who didn't know about those measurements. So he says the recession of the nebulae can't be considered as an isolated discovery. That is, you don't really know that the nebulae are moving away from you until you have a theory explaining how that works. So he says the movement of the spirals was not just consistent with the theory, but was foretold by the theorists. He pushes even further in claiming the expanding universe for theory. He admonishes observers for not realizing how much their observations rely on theory. I think Ken brought up one of his famous quotes along these lines earlier today. He says this many times, I like this one. For the reader resolved to eschew theory and admit only definite observational facts, all astronomical books are banned. There are no purely observational facts about the heavenly bodies. He probably was trying to needle Rutherford because he liked doing that sort of thing, but he says this again and again in many contexts. And he wasn't saying this to make the case that the investigators were on shaky ground or to say the observations weren't good. What he was trying to point out is that there were lots of different kinds of observations and theories out there that were relevant to these problems, and he needed to use theory to weld them all together through, to make sense of different lines of research. Because studying the whole universe is a tricky business, as it turns out. I think we've become kind of complacent about it nowadays. But back in the early days, it was really an almost terrifying idea to write down a theory and say, this is the universe, much less to look at a set of observations and say, I can determine what the universe looks like from that. So Eddington worked hard to encourage people to bring in sources from knowledge from all different sources, and to be okay with tentative knowledge. It's okay to explore a little bit instead of hoping for certainty all the time. Now, despite constantly arguing for the importance of theory, he wanted to stress that the idea of the expanding universe wasn't just a hazy-eyed speculation about the nature of things, which is an attack that observers would occasionally level. And he understood that observers and classical astronomers were, quote, not likely to be moved overmuch by ideas of bending of space or the gauge invariance of the Riemann-Christoffel tensor. Now, what he was referring to there is the fact that the mathematical apparatus of general relativity was completely foreign to the vast majority of astronomers and physicists at the time. He only knew it because of this peculiarity with the way the Cambridge tripos worked, that his coach had to teach him how to do very specific mathematics. So there were very few people who could actually tackle the math. And even worse, categories like curved space-time seemed downright metaphysical and not the sort of thing that an astronomer sitting at a telescope should be thinking about. So he wanted to remind astronomers that they should be interested in the ideas about the expanding universe, and that came back to Schleifer again. He said, look, you may not be interested in relativity, you may not like Einstein's ideas, you may not be able to do the math, but at the end of the day, there's a bizarre phenomenon out there, and we have an explanation for it, so you should listen to us, and you should care about what we have to say. Lemaitre's results emphasized another interesting cosmological result that was very important for Eddington, and that was the instability of the Einstein universe, as we mentioned a couple times today. So what Eddington was interested in is this idea that if you have an Einstein universe that has a static cosmological model, if it's disturbed, if you poke it in some way, it'll begin expanding and thus reproduce the observed motions of the spirals. Now, he thought this was very useful for a number of different reasons. He put a number of his research assistants to work studying what could cause these kind of disturbances. They eventually conclude that it was probably diffuse gas collapsing into stars and forming galaxies as well. So this model is sometimes called the Eddington universe, in which you start with an unstable Einstein universe, and it just sits there as undifferentiated matter for literally unknown amounts of time. And then at some point, stars begin condensing or something else happens, and then it begins to expand along the lines of the Lemaitre model. This particular model, in which you have indefinite time of stability and then sudden expansion, had a further appeal to Eddington in that it avoided a cosmological topic that he found quite problematic, and that was the question of the beginning of the universe. So people had started rewinding the clock of expansion, and this has raised the question of what the universe was like when all the galaxies were in close proximity, and even before that. This is when Lemaitre proposed his fireworks model, of which I won't say more. The idea there's this primeval atom that had all the matter in the universe that then exploded in this sort of quantum radioactive effect. And Eddington rejected this idea completely. He said, philosophically, the notion of a beginning is repugnant to me. And in particular, he said he didn't want anything that seemed to require a sudden and peculiar beginning of things. He wanted instead a natural beginning. So the advantage of his disturbed Einstein model was that, quote, the initial small disturbance can happen without supernatural interference. That is, it happens all just on its own. And he sums it up this way. He says, there is at least a philosophical satisfaction in regarding the world as beginning to evolve infinitely slowly from a primitive uniform distribution in unstable equilibrium. Hence, this case is the most attractive. Unfortunately, this was not quite enough for Eddington to be able to escape having to talk about beginnings. Even though his model avoided an initial explosion, there were other pressures for a distinct start to the universe, and this was the idea of a thermodynamic suggestion of the creation, the idea that if you run back the clock, eventually you'll get to a point of minimum entropy that must have been some kind of discontinuous beginning. This is an idea that goes back to the middle of the 19th century. Lord Kelvin particularly proposed it. So he describes it this way. He says, so this idea of a minimum entropy should be regarded as the working hypothesis of thermodynamics rather than its declaration of faith. It is one of those conclusions from which we can see no logical escape, only it suffers from the drawback that it is incredible. As a scientist, I simply do not believe that the present order of things started off with a bang. Unscientifically, I feel equally unwilling to accept the implied discontinuity in the divine nature, but I can make no suggestion to evade the deadlock. So he ends up concluding that views about the actual nature of the beginning of the universe are simply beyond scientific argument. And I think his use of the word discontinuity is key here. A discontinuity would mean that the event, the beginning, is not part of the world of uniform natural laws, which is what scientists actually study, so it simply couldn't be discussed in scientific terms. He preferred to talk about it as a kind of aesthetic feeling, and once described his position on the matter as he preferred a beginning that was not too unesthetically abrupt. So he argued that his static to expansion model was the best one for this, and certainly he said compared to Lemaitre's firework theory, he thought his ideas were more likely to satisfy the general sentiment of the reader. And he accepted that some would disagree, but in reply to those, he wrote, "Have it your own way, and now let us get away from the creation back to problems that we may possibly know something about." That is, he wanted to simply make the case that the nature of the beginning of the universe was so far beyond the comprehension of both humans and science that it was simply pointless to discuss. Now, a closely related problem to the creation of the universe is that of singularities. So Eddington didn't usually discuss the beginning of the universe in terms of singularities, and his general aversion to them might help explain why he was reluctant to allow a sudden beginning. The problem of singularities in general relativity appear very early, although they weren't usually called with that name. In Eddington's 1918 report, he's talking about de Sitter's model, and he first thinks about the slowing down at the edge of the universe, that at the very edge of the universe, time will stop completely, giving a singularity kind of effect. And he decided this was just a problem of point of view, since you could simply change the location of the observer, and the singularity would vanish then. A few years later, in Mathematical Theory of Relativity, he works out the math in a little more detail, and explicitly suggests that the de Sitter singularity at the edge of the universe is the same as the Schwarzschild singularity caused by mass. And he comments that since we can remove the de Sitter singularity through a coordinate transformation, we can probably remove all singularities that way. Right? Just move your origin not to the middle of the star, and you'll be fine. So by 1933, he seems to have decided that all singularities are always artifacts of coordinate systems and could have no physical meaning. So he's really not willing to discuss them in any meaningful way. I think there's another level to this as well, is that Eddington had a very sophisticated and complicated scientific epistemology, which, to sum it up really quickly, is to say that it's highly observer dependent. So very much the laws of nature actually depend on an observer being present to see them. So the idea that there could be a place closed off from observation was simply inconceivable. It wasn't even part of the natural order. This was probably also related to his thinking about collapsed stars in the 1930s, but I think that's a slightly different issue as well. Now, what Eddington would have considered his most important contributions to cosmology was actually something that was widely and completely rejected. That was what he called his fundamental theory. So Eddington was thinking about the big picture of cosmology in a very, very idiosyncratic way. He had this idea that there was a fundamental connection between quantum physics and cosmology, and in particular that the cosmological constant determines certain properties of subatomic particles. He invented a whole new calculus for working on this, and it depended heavily on these large number of coincidences, such as the ratio of the electrical and gravitational forces being similar to the total number of particles in the universe. And he tried to develop essentially a unified field theory from this. So he saw the cosmological constant, he called it the cosmical constant, as the key to the unification of all physical forces. In particular, it set a universal radius of curvature that controlled the size of electrons and protons and indirectly the behavior of electromagnetic phenomena. So the theory needed this closed universe with very particular properties, and he suspected he could derive the essential properties of the universe, such as the radius of curvature, the magnitude of the cosmical constant, and the total number of particles in the universe from a priori considerations such as the degrees of freedom of the electron, claims for which he was vigorously criticized and his ideas pretty much faded into obscurity. But I would emphasize that he thinks this is what's really important about studying cosmology. So in his book On the Expanding Universe, in the introduction, he says, this is a book about the expanding universe, but I deal with it not as an end in itself. To take an analogy from detective fiction, it's the clue, not the criminal. The hidden hand in my story is the cosmical constant. So that is, to him, the important part about expanding universe theory is that it had given a window into these deeper issues of the unification of astronomy, relativity, and quantum mechanics. The cosmology itself he saw as secondary, and he declared that it had given rise to no new philosophical issues. So to conclude, sort of from the framework of the whole conference, did Eddington have any importance to the story of the expanding universe? He certainly did not discover it in any sense. He didn't perform the relevant observations. He didn't develop the core theoretical models. But I think he was probably still critical to the story. He was a central clearinghouse for theories and data. As people have been pointed out several times today, his publication of Slipher's results are the ones that everyone uses for a decade. He's one of the few people who understand all of the astronomical and physical aspects of cosmology. So there's probably 3 or 4 people in the 1920s who actually know the astronomy and the physics and the math well enough to actually contribute to the problem. Eddington also made the case for the importance of theory in studying the universe. So whether you like it or not, he's one of the people who made cosmology something you could do at a desk, okay, with a pen or a pencil, or nowadays with a laptop, I suppose. He was very important for understanding the physical understandings of what general relativity meant and how to interpret the core concepts. And finally, he showed that many of the basic categories of an expanding universe were not obvious or necessary. For instance, the simple idea that redshifted spirals clearly indicated an expansion was not at all clear to the parties at the time, which of course complicates the notion of the discovery of the expanding universe as a whole. So I think I would want to say that Eddington is both central and marginal to the story, which is probably a good relativistic point to end on. Thank you very much.
5 minutes for discussion. Actually, he was a very strong defender of the cosmological constant. He said he would rather go back to Newton than give up cosmological constant. And in that respect, he was very much the friend of Lemaitre. Whereas Lemaitre also defended the cosmological constant, but for different reasons. You mentioned the one for Eddington. For Lemaitre, it was the force that helped expand the universe. And I think, and it was fascinating. The Eddington, he hated this Big Bang idea of Lemaitre. And I suspect, that's what we say also in our book, I suspect he was probably suspicious of Lemaitre because Lemaitre was a priest and he might have feared that he tried to smuggle in God somewhere.
It's conceivable. I should say Eddington was deeply religious himself, but in very different ways than Lemaitre. And Eddington wrote extensively on the nature of religion and science and did not feel that you should be able to see the action of God in the universe. So that's quite possible.
But then Lemaitre's answer was really the beginning of the world from the point of view of quantum mechanics. So Lemaitre made it quite clear that he didn't try to smuggle in God there, but he wanted the laws of nature to be found, not from the Bible, but from peoples like him or Eddington, of course, whom he
which I should say was the Orthodox.
It's not the dialogue between us. You wanted to say.
If I could just add to Harry's point, you make a great case. I think Eddington made many contributions but he made one very negative one. I think that phrase, not with a bang, first of all, it's very unfair, because Lemaitre is talking about quantum uncertainty, actually. That's the phrase he's using when he's talking about the beginning as such. But secondly, as you all know, then it gets picked up 20 years later by Fred Hoyle and spread to the public through a radio show. And some of us spend our working lives trying to explain to the public that the theory is not about a Big Bang. So, you know, I think it's just, there's a lesson for us all in science. If you allow your model to be labelled by its opponents, you always end up with this reductio ad observatum. You end up with a silly name, you know, and it's most unfortunate, you know, it really is.
He had a name for the model. They just took somebody else's name. He called it the primeval atom. He had a name for the model. He didn't let him name the model.
But again, on Lemaitre, he's very, very careful about that when you're talking about the instant at which it all begins, when he's talking, before even the primeval atom, he says, you go into a cloud of quantum uncertainty. And he uses that expression, a cloud of quantum uncertainty. Bang.
Yeah. That's right. Well, I think that's good advice for Mike.
Initial
your enemies label you.
When Eddington, it was a big problem how to get out of Einstein's unstable of the static model, because they had to start the expansion somehow. And Eddington got his PhD students, as you mentioned, he got them to work on it, Lemaitre worked on it, and they didn't find a solution to it. And they, I think McVitie in the end said, well, why should we torment our brains on it? After all, we see that it happens, so okay, doesn't matter how it started, it happens. But other, yes?
It's interesting that in 1923, in Eddington's book, called Geocount, he knew that test particles had separated. And yet at that time, he didn't predict that there would be a linear distant fringe information.
It's not, that's right.
It's understand you'd missed the linear part if you didn't realise that the model was non-static.
Right. He certainly didn't draw that. Yeah, whether or not he very rarely talks about precise quantitative relationships in this sense. So he generally talks about redshifts, sort of capital R, but the particular dependence of the redshift is not something he brings up very much. And I'm not quite sure why that is. My best guess, is quite speculative, is that he doesn't want to bug the observational astronomers with those mathematical details. It's like, guys, just look for redshifts, okay? Tell me if you find anything interesting. And we theorists over here, we can deal with the fun stuff over here. That's very speculative.
So you said there were 3 people that you thought understood the sorry. You said there were 3 people you thought understood the theory and the observations. I think we've talked about this before.
Yeah.
Certainly you mean Eddington, Lemaitre, and
de Sitter, I think.
Yeah. But what about Robertson? I mean, what about the other students of Eddington? Are we
that's
sure it's
I should say no. By the end of the 1920s, there's a large number of people.
You said around 1930.
If I did, I was being sloppy, so forgive me. I'd say by the mid-20s, there's still a few people. And actually, so I think the characteristic those people have is they have training as astronomers, they have extremely complicated mathematical backgrounds, and what's I going to say? Oh, they have a route back to Einstein. So this is quite important, actually. So when the field equations first got published, it's very hard to understand what's going on. So de Sitter makes a bunch of trips back and forth from Leiden to Berlin to talk to Einstein about how to use these equations. And it takes him, I don't know, it's the better part of a year going back and forth before he feels confident in doing it. And then he tries to sort of encapsulate that and send that to Eddington. And then it still takes Eddington a year to figure out how to manipulate GR. Again, seems so basic to us now, but even Einstein early on had trouble with his own equations, like trying to figure out the light deflection. So it's this sort of core group that got sort of word from the master, and then also had astronomical experience. And then in mid-20s, then we get textbooks like Mathematical Theory of Relativity. People start teaching classes, and you can actually learn these things for the first time.
They also got astray because they started just to talk pure mathematics, you know. Well, the transformation, coordinate transformation, they thought that they could solve problems in that way.
Yeah, it's like a whole other branch of relativistic thinking.
They didn't really know how to interpret the whole this cyclical. And Schleifer comes in again. If Schleifer's redshift hadn't been known, they wouldn't have talked about this
I think that's right. It would be, that's right. De Sitter would just be sort of one of the things
one
over
of the
there.
crazy
It's a weird
ideas.
theory.
Yes, I think your conclusion was very good when you.
You have to talk louder.
When you said that Eddington had two faces. He was not a discoverer, and he still contributed. It seems to me he had a good taste for good mathematics on one side, and had no intuition on what is going on in astronomy, in universe. In fact, he jumped on any explanation which provided Weil or De Sitter. Any new idea was immediately picked up by him and discussed widely. But I think he realized that a truth hides in a good mathematics. And when he saw that Lemaitre suggested something more or less clear and straightforward, and he accepted it immediately.
Yep. You willing to accept that?
Okay, I think we have to stop here, except if there is someone who has some fundamental comment or announcement. Is there anyone who wants to announce something?
Mike, what's the next event on
Yes.
the
Dinner, 6:30.
Dinner is at 6:30 at the room floor.
6:30 in the room next door.
Yes, and remember that Don Lago will speak to us a bit. Instead of giving his talk this morning, he's going to talk at the dinner. And Alan, grandson of VM, will also give us a chat. So see you all in about 30 minutes.